I thought there were a lot of talks on liquid crystals, and so I thought I would talk about a related area, also a little bit different maybe than some of the other talks, in that the liquid crystals that I'm interested in are really kind of localized, they're interfaces. And so the partial ordering basically is that you end up with these two layers, basically something like a smectic A, or you can think of it as a smectic C depending on the situation, where you have two layers, so you have a bilayer structure, and these bilayer structures form interesting geometries, and in order to study transport properties, it's very important not only to think about the hydrodynamics within these layers, but also the hydrodynamics in the bulk three-dimensional fluid surrounding these layers. If you treat it as purely a two-dimensional fluid, you end up with things like the Stokes paradox, which I'll talk a little bit more about. The thing that I'm interested in is looking at not only continuum mechanics models, but also models that are motivated by molecular simulation, so that we have kind of this ability to benchmark against a sort of more or closer to first principles description. The challenge there, of course, is that you can't do fully atomistic molecular dynamics simulation and access those kinds of large and interesting length scales that I'll be talking about in this particular presentation. And so I'm going to talk about these coarse-grained models, and what's interesting there is there's a challenge of how to, again, get into the models the role of that bulk solvent fluid. And so I'll discuss this fluctuating hydrodynamics approach as a way of kind of thermostating these coarse-grained MD models, which I think could be useful in a lot of other problems, namely in liquid crystals where you don't necessarily want to resolve the solvent explicitly. So I'll say a little bit about backgrounds. I think in this audience there's a lot of expertise in the chemistry associated with liquid crystals and in things like lipid bilayer membranes, but just for the sake of completeness, I'll say a few words about that. So lipid bilayer membranes obviously are very important for biological reasons. They form kind of the main boundary that compartmentalizes the cell from the outside world and also into these distinct cell organelles inside. Tremendously complicated processes occurring on with budding and fusion, things like the Golgi apparatus, package proteins, right, for shipment to different parts of the cell. The physics of that, of course, is incredibly complicated, so I'll be talking about much more simplified systems. But as a starting point, I mean, even understanding, let's say, a pure lipid bilayer and its mechanics and hydrodynamics is still kind of an interesting and area with lots of open challenges. So the sort of key outline is that, as I mentioned, the lipid bilayer compartmentalizes the cell. There's very dynamic structures. They play very diverse functions. The key point that I want to make from like a mathematical modeling point of view is that these are in kind of this combined fluid elastic phase. They're fluid in the sense that any deformation in plane is just resisted viscously, whereas any deformations out of plane basically respond elastically. And that's due to the nature of these interfaces where bending elastically, they bend elastically because when you bend, basically the amphiphiles that make up the layer have more exposure to the solvent, is at least the thinking. And in plane, you don't have resistance because that's mainly due to the rearrangements of the internal lipids. So these phenomena span very wide length and time scales. And as you can see in this biological example, treating everything as continuum mechanics might throw out sort of the baby with the bathwater in the sense that you're very interested in how proteins interact locally with lipids, rearrange the local ordering of the lipid, because the length scales are comparable between the protein and the bilayer width. So the presence of something like a protein in the bilayer changes fundamentally the sort of nature of that surrounding fluid, at least locally. Okay, so they're comprised of these amphiphilic molecules. You could think of this phosphoglyceride as one example. The key point from, again, a modeling perspective is that the sort of two interesting features of the chemistry. You sort of have these polar head groups that like to interact with water, so they're hydrophilic, whereas you have these tails that are nonpolar, and they tend to be energetically disfavorable to be in contact with the water. And so by putting these together in one molecule, there's sort of this competition. And so if you put these in water, they will tend to collect, for example, at an interface if you have water and air. If you have a high enough concentration and they're in the bulk with no interface to escape to, they'll tend to push their tails together to kind of shield the tails from the water. They expose the water-loving head, and you get things like micelles. And then if you have larger concentrations, they'll tend to form these bilayer structures. So it's effectively this partially ordered structure. You can think of it as a lyotropic liquid crystal because it's temperature dependent and concentration dependent. That plays a role in the phases that you get. And it's basically like an analog of like a smectic A phase, right? Because you have orientational ordering and layering and the orientation is essentially orthogonal to the layer. So the disorder in the system is mainly the X, Y, or in-plane translational configuration. And so that's where you're getting the fluid response. And when you bend, that's this maintain of the layer is where you're getting the elastic response. So the lamellar sheets are probably the most relevant for a lot of the biological questions that come to mind, but there's also a very rich phase diagram. In particular, chemists like to study making amphiphilic molecules that have things like fairly large hydrophilic head group, right, versus the tail. So it's not quite the picture I showed you on the previous slide. You kind of reverse it where the polar part is huge and the hydrophobic part is very small. And if you do that, you can get these really interesting hexagonal and cylindrical phases, very beautiful geometries and topologies. You can do something similar where you have a short hydrophilic head group and then a long, you can have a short hydrophilic head group and a long hydrophobic tail. And in that case, you get, again, these kinds of things like inverted micelles and sponge-like phases, et cetera. And if you have the short hydrophilic head group and long tails, there's a much larger part of this phase diagram, which is lamellar. And I'll mainly be focusing on this case, but wanted to point out that some of these other phases might be of interest. And of course, lipids have applications in stabilizing household products and things. Oh, the XY. I believe it's like concentration versus temperature, because these are lyotropic liquid crystals. Yeah, unfortunately, I don't have the resolution here. So I'm going to mainly talk about the lamellar phase, where you have short hydrophilic head groups and long hydrophobic tails. And so there's many ways you can go about, obviously, modeling liquid crystals at the molecular level all the way up to the continuum. And as I said, I'm interested in trying to bridge those two realms. So you could do fully atomistic molecular dynamics, but I think you can see from that previous phase diagram, you'd have a hard time getting to those length and time scales where you'd really access those rich kind of topologies and geometry. But nonetheless, this is very useful if you're looking at local effects, such as a protein interacting with a bilayer. There are now models where people have done a tremendous amount of work and studies to sort of coarse grain the molecular and also the solvent degrees of freedom. And so these are things like Martini models. And so you still keep the solvent explicit, because it's really this hydrophilic effect that's driving the structuring of the bilayer. And so if you remove the solvent, right, that free energy of interaction between the molecules, which is mediated by the solvent, would no longer arise. So there's a way to coarse grain, and this allows you to get to much larger length and time scales. But if you think about it, you're really interested in a lot of the dynamics occurring in a two-dimensional interface. But by having explicit solvent, you're still having to solve degrees of freedom that's spread out through this three-dimensional bulk, which is still computationally quite expensive. So to go a step further, you could try to figure out the effective free energy of interactions in a very simplified model of the lipid molecules. And these are the so-called implicit-solvent coarse-grained models that have become very widely used to study things like viruses binding to bilayers and different types of fusion processes. And so the atomic groups, again, are represented by these coarse-grained units, and then you do a kind of analysis. Oftentimes, it's a somewhat phenomenological kind of physical modeling, but you can certainly run molecular dynamic simulations and compute free energies that you then use to motivate interactions between parts of this. This is a 3-bead representation, where you have hydrophilic head interactions and hydrophobic tail interactions that are long range to kind of mimic this hydrophilic effect that would be occurring from the solvent, which is now missing. So that works very well for studying many equilibrium problems. You can show that you get very nice phase diagram. You can look at gel phases and fluid phases and things like self-assembly of the bilayer. But there are some issues, of course. When you remove all those atomic degrees of freedom, you are in some sense smoothing out the free energy landscape, so you have to be a little bit careful about some of the kinetics. You're obviously changing the entropy of the system because you've removed those degrees of freedom. But like I said, it works very well for many equilibrium problems. However, if you no longer have the solvent degrees of freedoms, if you look at the dynamics, if you want to look at something like protein diffusion in the bilayer, that no longer really accurately reflects the physics, because as I'll show in a little bit, the bulk fluid mechanics plays a role in the particular mobility responses you get. It's not just the hydrodynamics of the two-dimensional plane. And this goes back to work by Safman and Delberg. And if you're familiar with the fluid mechanics, you get the so-called Stokes paradox if you look at essentially a 2D disk immersed in a purely 2D fluid. There's no steady state velocity, because in some sense, mathematically, it's like you're looking at a three-dimensional fluid with right, translational symmetry in the z direction, like an infinite cylinder, right? So there's some length scale where the bulk three-dimensional solvent plays a role in regularizing, getting rid of that logarithmic divergent that occurs in Stokes' paradox. And that's missing, of course, in a purely implicit solvent description. So what I want to talk about is how to use these implicit solvent coarse-grained models, which allow you to get to very large length and time scales, but to extend them now to be used for kinetic studies by using continuum hydrodynamics to account for those missing correlations or hydrodynamics from the surrounding bulk. And in particular, because this is a molecular system, right, thermal fluctuations are playing a very important role. And so we have to have a way of essentially doing fluid mechanics calculations, but with fluctuations consistently incorporated. And so I'll discuss how I'm going to formulate this fluctuating hydrodynamics style thermostat. And so there's a lot of work that we've been doing over the years on this, building up towards these biophysical problems. And so you could also go, as I mentioned in the modeling, to a purely continuum mechanics description. Again, the challenge there is, should you treat things like proteins or inclusions as a continuum field on the surface or as discrete entities that bind to, let's say, a continuum sheet that you use for the bilayer. So we've done some work on these sort of hybrid particle continuum models, and they exhibit very rich and interesting behaviors. Okay, so that's mainly what I'm going to focus on in this talk. And I think a lot of the techniques that I'm going to mention would be applicable to other problems in soft materials. And we have had in the back of our mind looking at liquid crystals and things like that, where we think this might be an exciting simulation approach. So I'd be very open to talking to people that might be interested in collaborating on that. So I think in this audience, I won't say too much about that, the key features of soft materials. I mean, we're dealing often with systems that have interactions on the order of the thermal energy. You're very interested in this balance between the entropy and enthalpy of the system, which determines oftentimes the important features of the phase. And the main point I want to make is that I'm going to focus on the important roles that solvent plays. And so I already kind of talked about the different modeling length scales, at least from a molecular perspective, that are often used. And there are a lot of different thermostats that are also developed depending on what features of the system you're interested in studying. If you are mainly interested in equilibrium properties, there's a lot of artificial dynamics that you can use that will relax much more rapidly than if you tried to resolve the detailed kinetics, things like the Beredson or Noisy-Hoover thermostats. But if you're trying to study things like I mentioned protein diffusion or other kinetic effects, these don't really capture the right physics. They're capturing the equilibrium properties correctly, having as their invariant measure the appropriate Gibbs-Boltzmann distribution for the ensemble. Langevin dynamics is often used. That's where you have a local drag. And that works pretty well for certain problems. But as I'll mention, for things like protein diffusion, it really is important to get the bulk solvent hydrodynamics into the problem. So I'm mainly going to talk about incorporating these solvent-mediated kinetics. And some of the work we've done also is looking at other ensembles, some of which are not technically equilibrium ensembles, things like constant shear, volume, and temperature, or things like equilibrium ensemble where you have constant number, pressure, temperature. There's all kinds of interesting challenges in doing that in one of these finite simulation domains. Let's see here. Okay, so I talked kind of about the models and the ideas so that we can get to these much larger length scales and time scales, which would be relevant to problems in biophysics. So what I would like to do is leverage a lot of the techniques that have been developed traditionally for doing computational fluid dynamics, but to bring those down to being applicable for mesoscale problems. In particular, solving the fluid structure interaction problem, but not in its full detail because that can be very expensive. So there's a sort of class of techniques which I've been working with, which is the immersed boundary method. And this has worked very well for capturing fluid structure interactions in macroscopic systems. So I just give two examples here. Someone has done a very beautiful simulation of a hummingbird flight, for example, and blood flow in the heart. Of course, here the Reynolds numbers are much different than what you'd have in a biophysical system or something relevant to lipid bilayer membranes, but nonetheless, a lot of the ideas can be transferred for how to handle the fluid structure interaction in a way which is tractable. Now, the important thing, of course, is if you look closely, this is just showing a little example where the spontaneous curvature of the bilayer has been changed through an optical means and some clever chemistry. And you can see that thermal fluctuation plays a bit of a role in overcoming energy barriers and in the correlated motions, right? The hydrodynamics and thermal fluctuations together in the correlated motions of the bilayer. And so we'd like to capture fluid structure interactions, but you see a key point is having thermal fluctuations incorporated. And so we'd like to take things like that lipid model and leverage things like these immersed boundary techniques to handle the long-range hydrodynamic coupling and do that in a way where we fold in thermal fluctuations to obtain an effective molecular dynamics thermostat. And so that's sort of the key idea. And there's many approaches that are taken in fluid mechanics to handling fluid structure interaction. It's a very well, obviously recognized and appreciated problem because it arises in so many different contexts. So if you had something like airflow over a wing, you might model your fluid structure interaction through essentially a traction stress on your elastic structure, and then have a separate equations that you solve, for example, using finite elements. And then you basically balance the traction stress and the internal stress to look at deformations and to get feedback on the flow. Another approach, which is often used in like colloidal physics, is to basically boil everything down to an effective hydrodynamic coupling tensor. And there, that works very well if you have a lot of symmetry in the problem. You can analytically often derive these hydrodynamic coupling tensors and look at things like torques and translational responses. Of course, that becomes a challenge, right? If you're going to do the traction stress, you have to kind of mesh all the way up to the detail of the microstructure. And for hydrodynamic coupling tensors, if you have any type of polydispersity or internal degrees of freedom between your particles, that also becomes quite challenging because you don't necessarily know that analytically in advance. So we're going to kind of take a hybrid between these two approaches, and we're going to use a mesh to basically represent the hydrodynamics and use a lot of the traditional CFD solvers, but allow these sort of abstract operators, which I'll call lambda and gamma, to kind of model at some coarse-grained level the fluid structure interaction. And so one of the most widely used approaches for doing that, at least at a very, used on a lot of interesting problems, works quite well in practice, is to use these effective coupling kernels, which I call the Peskin delta function. It's just a smeared out delta function that has certain features to make it sort of numerically convenient, for example, having translation invariance. And you basically can take a force that applies to a particle, spread it out on your mesh, do the fluid solve, and then obtain a velocity, and then average according to using this approximate delta function. And if you go through the analysis, you can show that does a pretty good job in capturing a lot of the mobility responses that you would expect if you had done the more detailed types of calculations. And I'll show some examples of that in a little bit. Now, the key challenge here is we want to develop a thermostat that takes into account that fluid structure interaction, but you can see the fluid structure interaction model that I'm interested in isn't done with traction stresses. It's got sort of this level of approximation in it. So in some sense, what I have to do is go back to the hydrodynamic equations and rework statistical mechanics so that any type of thermostatting that I do takes into account those artifacts of the fluid structure model, that it's not a simple traction stress, as I showed in the previous slide, where I can couple two independent descriptions. So I want to point out some of the features of some of these other thermostats that are used. Things like Barrettson and Noisy-Hoover. Barrettson, for example, will basically redistribute the momentum between particles. And when you have Noisy-Hoover, you have this heat bath that you're transferring momentum between artificial dynamics. Langevin works well for certain situations where the dissipation and correlations are very localized. But in Langevin dynamics, you're not momentum conserving. You're missing a lot of the lateral correlations because this local drag law basically is a local sink for momentum, and then the thermal terms balance that, right? So that on average, you'll have, in some sense, momentum balance, but instantaneously, you don't have momentum balance. And this sort of sink and stochastic source kind of is missing these lateral correlations that you would have from a true hydrodynamic model. Of course, you can come up with a tensorial drag. That, of course, can be done, and that would be in similar spirit as what I showed in the middle there in that hydrodynamic coupling tensor slide. Well, you can make, this would be non-local in the sense that the coefficient or the mobility tensor might depend on the total configuration, of all the particles. Yeah. And so the approach that I'm going to take is to not use this kind of sink source approach where I'm locally killing momentum and then just balancing with the stochastic term. Instead, what I'm going to do is I'm going to introduce hydrodynamic equations. Basically, hydrodynamic equations are nothing more than momentum conservation laws, right? And so anything that any momentum that is lost from the particle then will be stored in the hydrodynamic fluid modes, and then I'll thermostat in such a manner that I can introduce back into the particle or structure degrees of freedom those fluctuations, right? And so roughly speaking, it has a superficial form that looks very similar to Langevin dynamics, but you're not taking your drag with respect to sort of like this ambient medium. here you can see this lacks a kind of Galilean invariance. Here what I'm going to do is I'm going to take my drag with respect to a reference velocity, which will be the reference velocity of the hydrodynamic field that I resolve. And then there's an interesting challenges in how you thermostat the overall system in a way that's consistent with statistical mechanics. And so this will allow me to capture those lateral correlations, because now there's momentum transport, for example, outside the bilayer into the bulk three-dimensional fluid, and then comes back in through things like the traction stress on the bilayer. Okay, so this idea of introducing fluctuations into hydrodynamics goes back to Landau and Lifshitz. And the origin of that, if you're not familiar of the fluctuations, is that if I put a particle, for example, in a fluid, if I go down to small enough scales, in some sense the fluid is a discrete material, right? And so you can think of this as your water molecules, and these are colliding, right, with whatever the microstructure is. And because it's discrete, there's an asymmetry where sometimes more of these molecules collide on one side than another, and so you get a little kick, and if you repeat that process, you get Brownian motion, right? And so the idea is to try to replace this detailed molecular model for the solvent with some type of continuum field. And that allows you all kinds of techniques in your simulation. I mean, in some sense you can filter, right, to only resolve scales that are of interest. You can also introduce additional effects such as keeping inertia or doing overdamped cases where you remove inertia. But essentially replacing that detailed molecular model for the solvent with a stochastic model is the idea. And so Landau-Lifshitz proposed one way to do that. Because in some sense the hydrodynamic drag and the thermal fluctuations arise from the same force, namely those collisions with the surrounding solvent molecule, you can use fluctuation dissipation considerations to derive a stochastic model that basically introduces a random stress. And the random stress, you can work out what its statistics are modulo a few particular postulates, like for example that you're going to assume that the random stress is a Gaussian random field, delta correlated in time, right? That those collision events occur very rapidly. And if you do that, you can, again, resort to those fluctuation dissipation considerations, and you can work out the covariance structure, the correlation structure of this random stress field, and that's given by what I've shown here, which is 2 times the fluid viscosity, basically KBT, the temperature, and then you have this particular structure that arises from the form of the stresses in the system, the dissipative stresses, which in this case are the Newtonian stresses. So if you work this out, you'll find that this satisfies the fluctuation dissipation balance for the system. So this introduces a random stress, and so now you have a fluctuating fluid. Now mathematically, right, so that works from kind of the point of view of the sort of physical modeling, but mathematically there's a lot of challenges because this has both delta correlations in time and in space. Yeah.
Dumb question. If I include stress in this form where I just have symmetrized delta functions for
yes.
the indices, am I enforcing incompressibility only on average?
No, you're instantaneously going to do incompressibility because the pressure will become also a stochastic quantity. Yeah, so this is introducing a random stress, and then each time, right, you basically impose the incompressibility that determines pressure. Yeah. So, I mean, the pressure is acting like a Lagrange multiplier on the system, on the mechanics. Okay, now this you can write down physically, but this has a lot of mathematical challenge. If you look, you're taking basically a divergence of a delta function. So this is worse than white noise, right? And we know that, so you would have a divergent, Fourier representation. So we know at some length scale, right, obviously the continuum mechanics is not holding, right, as you get down to molecular length scale. So there's going to be some interesting things to do to think about smart ways to regularize that. And also this is sort of formulated, if you were a mathematician, you think about this in the sense of like a distribution, right? That's how you convert delta functions into a rigorous mathematical concept. And you have things like the convective derivative there, and that's also problematic. So physically you could write this down, but there's some work you have to do to kind of, very carefully think about what you're trying to model so that you can regularize this to be something which is mathematically sound. And I'm writing this down here, and I can talk about those aspects of the problem offline for those who are interested. Now, what I'm mainly going to focus on is how to incorporate basically fluid structure interactions into this kind of Landau-Lifshitz fluctuating hydrodynamics so we can use it for thermostating. And so, as I mentioned, I'm going to mainly focus on this immersed boundary approach, although there are other techniques that can also be used. And so we have the fluid mechanics here, given by essentially the Landau-Lifshitz fluctuating hydrodynamics. You have the microstructure forces. And then for the microstructure kinetics, the simplest model, and you can do other things as I mentioned, is you simply advect the local, the particles given the local fluid velocity. So you kind of look around you and you see how the fluid is moving, and that's essentially how the microstructure gets entrained. And then any forces that are acting on your particles, and these models can be quite general. You just, you could do mostly soap, you could do whatever you like there. You then apply those forces as a force density in the fluid equations by spreading it out using the same kernel you used for averaging. And that turns out to be important. And you can show this captures, if you were to do this out, the effective hydrodynamic interactions you get by using these little kernels is essentially like the Rodney-Pargner-Yamakawa. Yeah. Oh, they do through a force law. Any force law you prescribe, yeah. But you won't get things like the hydrodynamic lubrication. Oh, there is. That's all here. Yeah, yeah. You can use any force laws you like. Yeah. So you could do electrokinetics with this. We're looking at some problems in that area, and you can do things like the coarse-grained molecular dynamics of membranes, as I'm going to show you in a little bit.
Is this equivalent to the you did it, and then I used to get the stress?
Yeah. So you can do things like that. If you had some, let's say, polymeric material that you modeled in this manner, yeah, you could do Irving-Cookwood for averaging over cut planes and. Yeah, and we've done cases where we've looked at something like an analog to less Edward boundary conditions, but in the context of fluctuating hydrodynamics. So the idea is you can basically use this as a thermostat to account for all those hydrodynamic correlations that might be missing in your coarse-grained model to do those types of kinetic studies. So you could study viscoelasticity, for example. So the key is, given this kind of approximate model for the fluid structure interactions, how do I introduce the thermal fluctuations? It turns out not quite to be as simple as the Landau-Lifshitz theory, where you just pop in the random stress. You have to be a little bit careful about the fact that you have these additional degrees of freedom. So the stochastic immersed boundary method, roughly speaking, is you're going to use this thermalized flow field. And one of the interesting twists that comes up is if you do the statistical mechanics carefully on this, you sort of realize at some stage in the analysis that the configuration degrees of freedom are not, in the Hamiltonian sense, the conjugates to the momentum degrees of freedom. And so what that means is that if you look on the sort of phase space, momentum configuration, you no longer have the usual Louisville theorem. Basically, because you're working with these generalized coordinates, you now have a metric factor, right, when the probability density is getting pushed around on the phase space. And so as a result, you get a stochastic forcing term that looks very similar to the Landau-Lifshitz case, but because of this basically the coordinates that you're using, you also get this thermal drift term. So you have to do the stochastic analysis very carefully of these stochastic partial differential equations in order to get consistency with statistical mechanics. And so there's this little drift term that arises from this kind of hydrodynamic coupling. And we'll see that come back when I look at the inertial formulation. And then you can write down the thermal forcing, again, using this kind of fluctuation dissipation concept, and you get this relationship to the Laplacian. If I had used a viscoelastic model or some other constitutive law for my fluid stresses, then there's a pretty straightforward way in which you can extend that, and then you'd have possibly thermal fluctuations that have memory and things of that nature in it. So this overall framework works quite nicely for a range of problems, and I'm showing you here the case when you use Newtonian models for your fluid. Okay, but now there's a number of challenges that arise if you actually want to use this in practice. One of them is you got to numerically discretize both in space and time. And the spatial aspect is kind of interesting. If you take kind of these traditional CFD approaches, such as finite volumes, which work very well, there's a lot of theory and experience with those types of techniques in the literature, you realize right away that the dissipation is very different for your discrete Laplacian on the mesh than your continuum Laplacian. And you don't want to just naively approximate the stochastic forces. You have to, in some sense, fine-tune the stochastic forces to the particular discretization that you've developed. And so you can use basically discrete fluctuation dissipation balance to get a correlation structure for these thermal random fields, basically the random stress. And if you do that, we've worked this out for the finite volume scheme as well as for different finite element schemes. You can ensure this fluctuation dissipation balance and get nice results, even reducing artifacts that you would have otherwise by taking more, let's say, physically motivated, phenomenological models for your thermal force at things like coarse refined interfaces. And so that works quite well. There's another issue which is maybe more serious if you want to do long timescale simulations, and that is the hydrodynamics itself introduces a new timescale into the problem. And so what happens if you do kind of these back of the envelope analyses, if I had something like a 10 nanometer particle, that's going to take me on the order of, let's say, 10 to the 3, 1,000 nanoseconds. And I'm thinking about, kind of physiological conditions, so water at room temperature is the parameters that I'm using for this estimate. And then the fluid modes kind of have a whole range of relaxation timescales depending on what wavelength you look at. So if you're on the order of 10 nanometers, that's on the order of 1,000th of a nanosecond. So you have a factor of 1,000,000 between the sort of fastest timescales in this dynamical system and the even an uninteresting event, which is just diffusion of a 10 nanometer particle, its own length scale. And so that's because the thermal fluctuations basically excite all the different hydrodynamic modes. And so the problem in some sense is tremendously stiff. And there's kind of two ways you could go about resolving that. I mean, one way is you could say, okay, I'll just try to be clever, develop some kind of stiff time-step integrator, do like an implicit method. You have to be really careful, though, because that is going to augment the fluctuations of the system. And so you'd have to be really delicate about preserving the statistical mechanical structure if you do something like an implicit method. We're going to show a technique that you can use called exponential time stepping to deal with the stiffness, leveraging some results from stochastic analysis. The other thing you could do is a perturbation analysis of the stochastic PDEs. Look at the backward Kolmogorov equations, do a singular perturbation analysis, then back out kind of reduced models where maybe you eliminate certain time scales or filter in some sense the fluid modes that you don't think are playing a big role in the dynamics that you're interested in. So I'll try to go through this. I mean, I would suggest looking at our paper if you're very interested, because it's kind of hard to put the details all up on a slide, but I'll give the basic idea. So we can write in sort of the more abstract language of calculus. You can write the fluid equations in this manner. So you can write it as differentials, and you tend to do that because technically you're not allowed to differentiate Brownian motion. It's a non-differentiable trajectory. And so what you can do is you basically work with everything in terms of integration theory. And so this is just the differential for the fluid velocity. This would be the Newtonian stresses, any microstructure forces, and this is a nice way to represent the thermal form so that we can see how it arises by basically correlating a bunch of independent Brownian motions. So if you think about the fluid mechanics discretized on a lattice, you go through that fluctuation dissipation prescription I mentioned, and that will give you a random field, and there's some correlation for the thermal noise driving the whole system. And you can always represent that Gaussian random field as a linear operator times a vector valued Brownian motion, right? So this would be the Cholesky factor of your correlation. So Q does not, it's not multiplicative in this case. Q depends on L and basically the energetics associated with hydrodynamics, which is basically just the kinetic energy, so you can work that out. And then you have the structure equations as well to deal with, and both of these are going to present stiffness. You kind of have these trajectories, obviously, that are very, have a lot of interesting time scales in them. And oftentimes what you're interested in, if you're looking at like that 10 nanometer particle example, is you're just interested in that particle moving 10 nanometers. You may not care about all the details that the fluid mechanics went through during that process. And so what we'd like to effectively do is replace all those intricate fluid dynamics with something that kind of captures what the effective statistical contributions of where the fluid are to the microstructure over, let's say, this little red window. And so I'll first deal with those equations. And so one of the things you notice that when you write it in this kind of abstract form is it's a linear operator of U, so you can essentially write down analytically a solution for U after a certain amount of time using essentially the method of integrating factors. And doing that in the context of calculus, you can express it in this form. So you basically have that the fluid state at time t is this exponential of your differential operator, in this case Laplacian, of the fluid state at time 0, plus this time integral of the exponentiating the operator against the particle forces. And then you have this stochastic integral, and that comes out from the Ito calculus. And so this would be interpreted in the sense of the Ito integral. And then there's some nice properties of this. You can think of this as the following. You have this exponentiation of the operator that kills the previous state of the fluid. If there was no forcing, this is what you would get. But you have the particle forces and you have the thermal forces. And it turns out, because of the nature of this integrand, namely that Q does not depend on U, this is a Gaussian random variable. And you can use Ito calculus actually to compute both its mean and its correlation structure analytically. And so that's what I'm going to do here, kind of quick. So if you look at the particle forces, one of the nice things you can do, if the microstructure and the fluid degrees of freedom really do have that separation of time scales, if the forces are configuration dependent based on where the microstructure is or what shape it is, and if it's like a polymer, you can treat that as effectively constant provided this time scale is not too large, right? And if you do that, then you can work out this integral exactly, right? And you end up with this nice expression for approximating the contributions of the force over the time scale 0 to t, damped out, by that differential operator L. And then you can do something similar for the thermal fluctuations resorting to Ito calculus, namely the Ito isometry, tells us that the correlation structure of that random variable to account for thermal fluctuations over the time step 0t is given by this, and you can work that out, and you can generate a random variate on the lattice that has those statistics. And so that gives you a, in the case of using Fourier method, it looks like this in terms of the Fourier symbols. And so that gives you a stiff time step integrator. So basically what you would do is approximate this term and this term using this expression and the random variate with that covariant structure. And these could be particularly high dimensional if you have a fluid lattice. And the fluid integrator then becomes basically taking your state at time n, exponentiating the operator, which can be done straightforwardly in in Fourier space, integrating up the particle contributions, integrating up the thermal terms, and that gives you the state at time n plus 1. And so that works pretty well in practice if you're on a uniform lattice, because everything can be done with FFTs. If you're on a non-uniform lattice, life gets a lot more complicated, but we've worked out ways of using multigrid basically to develop Gibbs samplers that can sample exactly these very intricate kind of correlation structures that come out of the mesh discretization. So that's one approach. Now, the second thing we need to deal with is updating the structure degrees of freedom. And the way that that can be done as a stiff integrator is, again, kind of using this idea of integrating in time the differential equation and then coming up with an approximate model for those temporal contributions over this window. And so this is just saying your particle configuration at time t, given your current state, is just the time integral of basically the moving average, right, of the fluid velocity, right, that you would have sampled between time 0 and t. Now, again, if the particle is not moving very much on this time scale 0 to t, you can approximate it as, using essentially the initial position. And so that gives you no longer a moving average, just a time average of the fluid velocity field, which then afterwards you average, right? So the leading order, that would give you an approximation of the new state of the microstructure. So you can, again, go through and do some Ito calculus. The key Gaussian variable you need to resolve is this I velocity of t, which is the time integrated fluid velocity from 0 to t. And so you can work that out. It's very intricate, so I wouldn't suggest trying to read all of these expressions. But basically, you can work out what the mean contribution is. It's given by this in terms of the previous fluid state and microstructure forces over the time. It's given by this interesting correlation. And then what you have to remember is that previous random variate that I used to update the fluid mechanics has to be correlated appropriately with this random variate that I used to update the microstructure, because they're basically the same underlying random field driving both, right? And so you can work out using Ito calculus that cross correlation, and that's what's given in this expression here. So putting that all together, that gives you a stiff integrator for integrating both the microstructure and the fluid mechanics, basically filtering out the high frequency modes of the system, which were the source of stiffness. Okay, and that works very well provided you're on uniform meshes. If you're not, like I said, we've recently worked on numerical techniques to deal with a lot of the issues with sampling these random fields and expressions using multigrid and other types of iterative methods. So that's sort of a summary then of the immersed boundary approach. And so you can do things like under-resolve the fluid modes. You can even go to the extreme of relaxing all the fluid modes on the timescales that you're resolving with the particles. And you'll recover something similar to like a Brownian and Stokesian simulation. But another utility of having the fluid there is you will pick up certain inertial effects that are in the fluid. And that might be important if you're looking at certain types of experimental data sets, let's say like X-ray or maybe neutron spectral data, scattering data. You may have signatures of inertia that you'll want in your particular coarse-grained model in order to try to tease out some of the effects. And so this is just showing a quick validation of that for Brownian motion. This is just relating it to basically showing the Stokes-Einstein relation holds even when you under-resolve the fluid mechanics. This kind of shows that we capture in our continuum mechanics description this very interesting phenomenon that was noticed by Adler and Wainwright in the 1950s when they started doing molecular dynamics simulations, namely of things like Brownian motion. They expected the velocity to come out with like a velocity autocorrelation to come out exponential, which is what's predicted if you use simply the Langevin equation, right? But when you do it with all of the molecular degrees of freedom, you in fact get a power law, which is t to the negative 3/2. And that was kind of mysterious at the time. And a lot of work has been done to explain that. And it turns out where it's coming from is the hydrodynamic modes in the fluid. There's a finite time scale for those to relax. So this is coming from essentially hydrodynamic memory, if you like. Right? So if a Brownian particle takes a fluctuation in a certain direction, it sort of drags fluid along with it. And it takes time for those fluid modes to damp down by the time scale for, let's say, the direction to reverse. And so if you play around with that, you can work out pretty straightforwardly analytically. You can back out this t to the negative 3/2 if you take into account all of the different relaxation time scales of the surrounding fluid. So there may be circumstances in which that could be of interest in your modeling. And then it's just to check on the equilibrium statistical mechanics. This is just diffusion of a particle in like a spherical potential, showing that you get the right Gibbs-Boltzmann statistics. And so you can extend this obviously to other coupling types and other regimes, as I'll discuss in a minute. And I'll bring this back to lipid bilayers in a few slides. So one way you can generalize this, if you're interested in other coupling operators, or maybe you want the microstructure degrees of freedom to have inertia, or simply that you're working with something like a molecular dynamics package and you'd like to use this as a thermostat, not the immersed boundary coupling, which is very tightly coupled to the local fluid velocity. You can introduce the two momentum equations separately. You could have the fluid equations here, the structure equations, and then have an effective drag between the two, which transfers momentum back and forth, similar to what I showed on the first slide. And so if you do that, this drag would then be introduced into the fluid equations as a local force density. So these operators, lambda, basically turn a particle force into a force density, similar in spirit to the immersed boundary method. And the operator gamma takes the local fluid environment and in some sense, averages it or does some other linear operation to it to determine for you a reference velocity, to determine the drag with respect to the particle. So capital gamma, you mean what is it specifically, or what does it mean? It's just averaging the local fluid environment, yeah. Hmm? Here? Which one, lambda, epsilon? So what lambda is doing is this would be my drag force, right? So I'm dragging the fluid around me, but you have to change from force to force density because of the nature of the conservation law. Yeah, it's a momentum conservation law for momentum density. Yeah. So this just is converting from, in some sense, like the, let's say, Lagrangian way of formulating the mechanics to the Eulerian. Okay. Oh yeah, and I wrote this down here. And then you have to thermalize the system in a way which is consistent given this kind of approximate drag law that you're using. And the nature of that drag law plays a particular role in the form of the thermal fluctuation. So this is how it works out for the fluid mechanics. This is how it works out for the particles. And then there's a cross-correlation terms because these things are obviously related. Right? So we're essentially replacing, again, like the molecular dynamics of the surrounding solvent with a continuum field. Right? And okay, so you can introduce different types of coupling operators. I'll just mention abstractly, there's a few kind of mathematical features you'd want them to have. The lambda, for example, should basically integrate to 1 so that you have conservation of momentum. And you'd like to have things like conservation of energy, at least that the coupling operator converting from Eulerian to Lagrangian is not a source of artificial dissipation. And so that can be done. You work out the time derivative of this, and what this shows you is that you should have an adjoint condition between the lambda operator and the gamma operator. And so that's tremendously useful in modeling because it basically tells you that if I know one of these, namely I know, let's say, the response of a particle to a flow, then it sort of prescribes for me that if I do an active force or torque on a particle, how I should do the force spreading to the surrounding flow. And so I'll show you an example. So the immersed boundary method, of course, has that property. And that's where a lot of these concepts were originally developed. And here, this is showing how you can use, abstract that idea to model, for example, a colloidal particle where you have, both rotational and translational degrees of freedom. So you know basically from things like the Faxon relations how that particle should respond to flow, and the adjoint condition gives you a way to spread forces or torques in the fluid. And then you can look at what hydrodynamic coupling tensors come out of that, and you can recover Rotney, Pragner, Yamakawa to a very good approximation, provided you're not too close, because you're not going to get things for free. You're not going to get the lubrication, for example. I mean, you could build a detailed particle model, right, with a spherical shell, and in that case, you would recover things like lubrication. But for just simply essentially a point particle, you will Okay, this also has numerical stiffness. As mentioned before, additional timescales enter because of that drag coefficient and some of the inertial effects. And so again, there's those sort of two approaches. I'll just quickly show you how you could use a perturbation analysis in order to reduce those equations. And so one of the interesting things you can do is take your stochastic differential equation. There's a way of representing it as a PD, basically for the statistic of evolution. So given that I start at x, what is the expectation of a function at time t of the process? That's given by u of xt, which solves this partial differential equation. This is known as the infinitesimal generator, because once you know that, you essentially know all the statistics of the system and how it evolves. You can do your singular perturbation analysis on the backward Kolmogorov PD. It's a bit involved to go over here in detail, but you do your singular perturbation analysis, and this gives you an effective operator. So you can get from L epsilon, as epsilon goes to 0, an effective infinitesimal generator, right? That gives you this, and then by reading off the coefficients, this gives you right, your reduced stochastic process. And so by doing that for our fluctuating hydrodynamics description, you can kind of put that, what I call SELM, stochastic Euler Lagrange method, you can kind of put a lot of different techniques all kind of in this unified framework. And so you have here, things like the immersed boundary method pop out, when you have very tight coupling, and if you relax, let's say the fluid relaxation timescales to be very rapid relative to the particle dynamics, you get Brownian Stokesian dynamics. And then you can use these various descriptions to develop different types of numerical methods. Okay, so I won't say too much about that, but just to kind of summarize that there's a way to deal with stiffness, even in that more general setting. Okay, so I'll skip this in the interest of time. You can do adaptive meshes. So let me come back to talking about these lipid bilayer membrane models. And I only have a few minutes, right? So as I mentioned before, I'm going to primarily focus on this model developed by Cook and DiCerno and Kramer. In particular, they've worked out for equilibrium the properties of this coarse-grained model. So we know how to parameterize it, basically at a nice fluid phase. There's this long-range tail that you can adjust, which is a key feature of the model that allows you to get a nice region of fluid phase within the phase diagram. There's some challenges in how you even come up with good models for the hydrophobic hydrophilic effect, which they've addressed nicely. And so using this kind of fluctuating hydrodynamic approach, we can look at self-assembled bilayers. And what we've been mainly focusing our attention on is trying to make a link between the molecular description and understanding the continuum mechanics of this molecular model when you tune for, let's say, different attraction strengths between the lipids or different geometries. Flat sheet versus something like a vesicle. And so if you look at the top, you'll see that this model self-assembles into these little disc-like shapes because that minimizes the contact of the hydrophobic part, and then you end up with things curling up to a spherical shape when they get to a large enough size, because there's a competition between the bending energy and this line tension around the disk. And so when you get big enough, basically the line tension wins and you fold up into a spherical vesicle. What is that? Yeah, blue is the hydrophilic head and the yellow is the hydrophobic tail. Three beads, basically. They're essentially like Leonard-Jones beads, but one of the key ideas that was introduced by Marcus DiCerno and his collaborators was to have this long-range tail, which basically gives you a little bit more flexibility than you would have in a Leonard-Jones-like law, which gives you this beautiful fluid phase, basically, as a large part of the phase diagram. Well, if you do Langevin, it would be local. If you do the fluctuating hydrodynamics, it would be correlated through the surrounding hydrodynamic fields. Yeah. So you can then study the kinetics of things like we could do things like proteins in principle within things like spherical vesicles, right? Things of that nature. And the nice thing about using a spherical vesicle versus a flat sheet is you don't have periodic artifacts and all those other issues. So we're getting up to length scales where we can start to deal. Yeah, and I sliced it just so you could see the structure. Yeah. Let's see here. So you could do flat sheets as well. So one of the things you notice right away is you can run the simulations with something like the Langevin dynamics. And if you were to do that, you basically, if you parameterize the diffusivity of the head group, for example, of the lipids, you don't end up with any real long-range clusters. So this is long-range correlations. This is showing like a little analysis where I take one lipid and I look at like a cluster of growing size, how they're correlated. And if you do the fluctuating hydrodynamics, you get nice correlations. There is a little trick you can play where you take the viscosity very small for the drag law, and then you do get some inertial effects, namely it's like billiard balls that do spread the momentum. Whoops. Okay. And yeah. I put this on here, but I'm still learning how to use. There we go. Okay. And I'll finish up because that's, yeah. And so what we've done is this correlation analysis where you can take a lipid, let the thing passively fluctuate as I showed you in the previous slide, take a lipid, look at its displacement or its velocity locally, and its correlation with the velocity of a lipid elsewhere. And you can relate that by linear response theory basically back to hydrodynamic equations. And so we've done that and shown basically that if you take Langevin with Stokes drag, you basically don't get any lateral correlations, right? No lipid flow. If you do the fluctuating hydrodynamics, again, parameterizing so you get the proper head group diffusivity, you get these long-range hydrodynamic fields. And you can play the, just for kind of fun, because this is done in the literature, just tuning down the viscosity, you get kind of this billiard ball effect, just for sake of comparison. And so understanding where these hydrodynamic flows come from is kind of an interesting problem. But like I said, through linear response theory, you can relate that to hydrodynamic equations. And so we've developed continuum mechanics and ways of processing our molecular simulation trajectories to be able to relate our coarse-grained models to continuum hydrodynamic fields and also bending fields as well. So we can relate using the spectrum, basically, or the correlation structure. We can relate that to a prediction from a continuum theory to then back out an effective viscosity and an effective bending modulus for the coarse-grained bilayer. So that gives us a key link between the molecular interactions and the continuum mechanics you'd ultimately have. And you'd want to do that as a first step for one of these biophysical studies so that if you're ultimately trying to relate to experimental data, you're in the right regime. And so this is just showing a little bit of the calculus that's involved in solving fluid mechanics on manifolds. We've recently put out a paper, it's available in the archives, using exterior calculus techniques basically to formulate the Stokes equations. And so this is too much, obviously, for me to go through now. The key point, though, is you can write down the fluid equations, Stokes equations, in a very elegant form using the exterior operators like the codifferential and the exterior derivative, which gives you kind of a geometrically transparent way of seeing the contributions of things like the curvature. So that K there, for example, is the Gaussian curvature. And you can extend many of the techniques you would use in fluid mechanics, things like velocity potentials, curl, and concepts of that nature that you might use to represent incompressible field to this context and solve the bilayer problem. That's what was done here. And I'll wrap up. There's some interesting things that happen relating curvature and shear, even for fields that are effectively constant given the local metric of the curved surface. And so these are just showing some results for the mobility profiles, and you can refer to our paper if you want, or we can discuss offline, which I'd be very happy to do. These are just showing how we can use these immersed boundary techniques to look at coupling between proteins that are either in the same leaflet or different leaflets, rotational and translational mobilities as a function of things like varying the viscosity or looking at things like varying the intermonolar slip. And there's some very, rich dynamics that occur, which I don't have time to go through. This is just showing you can also use the location of the vortex in principle to estimate things like viscosity of the bilayer. And so there's a few different strategies for relating those molecular level effects. And this is showing collective dynamics of a, just to give you one more thing if you're willing, just to show you the kind of rich collective dynamics that occur on a bilayer because of the finite geometry and the curvature. So anyway, I know I rushed through the last part. There's a bunch of other things that we're doing looking at fusion and lipid tubules using these techniques. And I think maybe in summary, I think there's a lot of exciting problems in soft materials that we can address with this new fluctuating hydrodynamic thermostat. And I'd be very happy to talk with people about other applications, or I'm very open to collaboration. I'll mention one other thing, which is we have you don't have to code this up from scratch yourself. We have a package that we've implemented for LAMMPS, and so that's available if you want to do your own simulations using these fluctuating hydrodynamic techniques. So thank you very much for your attention. Okay.